Okay, so I'm just going to record a short video explaining a particular question my students seem to have been struggling with. Alright, so first part of the question asks you to state the principle of moments. So this is the first condition of equilibrium, really. When in equilibrium, sum of clockwise moments is equal to the sum of anti-clockwise moments. So just a note here, in the examiner's report on this question, it's people didn't mention that it was the sum, and they weren't explicit that when something is in equilibrium, it's the sum of clockwise moments will be equal to the sum of anti-clockwise moments. So that bit should have been relatively straightforward. If you're struggling with it, it's a case of literally just memorizing the definitions. In the next part of the question, so to increase the extension of a stiff spring for a given load, a student set up the system shown in the diagram. The weight of the metal bar is 5 newtons. The tension achieved in the spring was 37 newtons. It tells you gravitational field strength, and it says apply the principle of moments to calculate the mass of the load the student used. Right, so we're looking for this value. First of all, I'm just going to think about what's clockwise and what's anti-clockwise, and where's the pivot. So the pivot is here. So you can imagine you're pivoting the object from here. The tension pulling up here of 37 newtons. You've got weight pulling down here of the bar. That's the centre of mass of the bar, and you've got the load here. So this is actually going to turn this thing anti-clockwise. If you think about a clock, that way is anti-clockwise and this way is clockwise. So this is an anti-clockwise moment. Okay, this is a clockwise moment, and this is a clockwise moment. So if we think about the definition we've just written down, the sum of the anti-clockwise moments should be equal to the sum of the clockwise moments. Oops. Let's write down that first step then. So anti-clockwise moments should equal clockwise moments. We've got one anti-clockwise moment, which is force times distance. I'll put that line in as well. Force times distance should be equal to, there's two clockwise moments, force times distance plus force times distance. So that's the sum of. The anti-clockwise moment will be 37 newtons times by a distance of 0.15 meters. We've got a clockwise moment here of 5 newtons multiplied by 0.45 meters plus a clockwise moment of a force, which we don't know, the force due to the load, multiplied by, I have to be a little bit careful here because the distance from the spring is very, very small and hard to see, and I think a few people made mistakes here because there's an arrow and another arrow, and it is, to be honest, very poorly drawn. It's very hard to see on the screen. So it's actually 0.7 meters plus 0.15, so it's a total of 0.85 meters in distance. I made a mistake the first time I did this question, doing exactly that. So now I want to rearrange for FL. So I can subtract 5 times 0.45 from both sides, so that gets me to 37 times 0.15 minus 5 times 0.45. Sorry, jumping ahead of myself here. Is equal to FL times 0.85. To get rid of the 0.85, I divide both sides by 0.85, which would cancel 0.85 on this side. Right, so FL will be equal to this value. So let's work out that force first. So I'll just get my calculator out. 37
times 0.15 is 5.55. Subtract from that in brackets 5 times 0.45. Right, is 3.3. Divide by 0.85 is 3.88. So
we have 3.882 newtons, or 3.88 newtons. So this is nearly there, because that's the force that this load is applying in the clockwise, producing a clockwise moment. But we're asked to calculate the mass. So it's a 4-mark question. There's a fair bit to do in it. The mass will be, well, if weight equals mass times gravity, or F equals ma if you prefer. Rearranging for mass, mass equals weight over gravity, so the weight is in newtons. So we're doing 3.88 divided by 9.81. Divide by 9.81 gets us a value of 0.395 or 0.4 kg. So that's the final answer, double underlined to make it clear. Okay, so the next part of the question, we've answered this one, the 4-mark question. The next part of the question is asking, calculate the magnitude of the force exerted on the metal bar at the pivot. So the pivot must be applying a force to this thing. So you can use the second condition of equilibrium to work this out, which you could just think of as being whatever's pushing up must be equal to whatever's pushing down. Okay? For the thing to be in equilibrium, the forces in the y direction must add up to 0, which is basically what I'm saying there. So we have 37 newtons up, we have 5 newtons down, plus 3.88 newtons down. Right, so you can see that this is not going to add up to 37. So we must have an additional force down that is coming from the pivot, right? A downward force. So we'll call that force P. So you can simply 37 minus 5 plus 3.88. Okay, so
5 plus 3.88. Okay, so we get a value of
28.12 newtons. Okay, so that's 28.12 newtons. Next, draw an arrow on the diagram to show the direction of the force calculated in part 2. So understanding the direction is important. Again, if you've got 37 pulling up, you've got 3.88 pulling down and 5 pulling down here, you must have an additional force pulling down here. So the direction we've thought about twice now. I've drawn the arrow on to show the direction of that force. Okay, answer is down, it's at the pivot. I have to draw it on the pivot like it says. Okay, and the final part says the spring stiffness has a stiffness of K, which is 500 newtons per meter. Calculate the energy stored in the spring. So this, if you look on your equation sheet, you'll find an equation for the energy stored in the spring is equal to half the spring constant times the change in length squared. Okay. What we need to do is find the change in length then for 37 newtons first. So there's another formula, F equals KL. So force equals spring constant times change in length. So let's find the change in length would be delta L will equal F over K. Okay, we've got a force of 37 divided by 550. So our change in length would be 0.067 meters. Now just sub this number into this formula. So half 550 times 0.067 squared, and just calculate that. And we get an answer of 1.244, etc. joules. So that's the energy stored in the spring. Okay, I hope you found this useful. If you have any comments, suggestions or feedback, please comment in the section below. Thanks for watching.